For question number 3, what you have to keep in mind for part A is that there are two dipoles that are perpendicular to each other. So you have the first dipole right here and the second dipole right here. To find the net electric field at location B, you have to consider the distance in the x and y direction. In the x direction, you have this length going this way, plus the radius r from a thin plastic shell, as well as the distance b to the location B. In the x direction, we have the electric field due to the thin plastic shell, as well as the electric field due to the parallel dipole. So we have the first equation, which is kq over r plus b squared for the sphere, and for the dipole that's parallel, we have k 2qs over l plus r plus b cubed. That's the ordinary equation for a dipole, but the only thing we changed here is distance because, as I said before, it goes from L plus the R and the B. In the y direction, we have the perpendicular dipole. It's the same here where we have the normal equation, and the only thing we changed is the distance R, which has been changed from L plus R and B. The net electric field, you have to keep in mind, is going to be a vector notation because it's acting in the I direction as well as the J direction. So we have the sphere and the parallel dipole in the I direction and the perpendicular dipole in the J direction. So the answer that we end up getting at the end is kq over r plus b squared plus 2qs over l plus r plus b cubed in the I direction, and the kqs over l plus r plus b cubed in the J direction. For part B and C, you were supposed to draw and label the collection of electric fields at location A. Location A is now inside of a neutral metal ball at a distance B inside. For this part, you're supposed to draw the electric field at location A, and the way you would draw the electric field at this location would be an electric field due to the perpendicular dipole as well as the electric field due to the parallel dipole. So the electric field due to the parallel dipole would point in the towards this direction, so it would go like this, and the electric field to the perpendicular dipole would go like this. I'm sorry, the electric field due to the parallel dipole would point in this direction, and the one in the perpendicular would point. The parallel would point in this direction, and the perpendicular would point in this direction, which would give you a net electric field pointing in this direction. The electric field this would cause an electric field due to the E-ball pointing in the opposite direction, so that the total charge of the E-ball can be 0. The charge distribution due because the two positive dipoles are here would result in 3 negative charges here and 3 positive charges here. You have to be careful that you have equal and opposite charges because the net electric field of the neutral metal ball is 0, which answers part D. Thank you.